Our next speaker is Skyler Palatnick from UCSB, and he's going to tell us about his work on metasurfaces. There you go. All right, take it away.
All right. So hi, I'm Skyler. I'm a fifth-year grad student at UC Santa Barbara, and I'll talk to you about the work I've done over the last couple of years to develop metasurface optics for imaging exoplanets. So at this point in the talk, I hope we all know what exoplanets are, why they're cool, and also that there is a proposed mission, the Habitable Worlds Observatory, with the plan of imaging Earth-like planets around sun-like stars and characterizing them for signs of life. To do so requires a coronagraph, or a starlight blocking instrument, that can achieve 10 to the minus 10 contrasts over a bandwidth like 20%, so we can actually resolve Earth-like planets and characterize them for signs of life. There's a variety of different architectures for chronographic systems, each with their own pros and cons, and there's also a variety of different chronographic masks, or starlight blocking optics, that are used. The one that I'll focus on the most in this talk is a vortex chronograph. So the vortex chronograph works by focusing starlight on the center of a vortex phase mask. This looks like the subimage B, and it applies an azimuthal phase gradient to this incident light, which transforms it from a flat wavefront at the input to a ring-like shape at the output. This casts the light outward, where it's collimated by a lens, and assumes that classic ring of fire shape you can see in subimage C. This propagates to a leostop, which is an aperture chosen to, for a perfect vortex, perfectly suppress this light. If you're a planet, you're going to be focused off the center of the vortex, and thus see a much more gradual phase shift when you pass through the vortex. That means that you won't transform into a ring, and you can pass through the open aperture of the leostop to be resolved on the detector. In theory, a vortex coronagraph can get contrasts well below 10 to the minus 10 at inner working angles that are small enough to resolve Earth-like planets around sun-like stars. However, in practice, it's been much more difficult. The best current vortex chronographs have all been made with liquid crystal technology. This is geometric phase optics that operate on polarized light. Contrasts in the lab have been around 10 to the minus 9 at the best at Caltech. But to do better, there's some obstacles that need to be addressed. First, there are aberrations that can affect different polarization states of light differently, which can degrade vortex performance. Second, these are expensive and difficult to manufacture optics, and there's really only a handful of vendors, and at their high price point, they come with defects that contribute to a leakage term. This term corresponds to light that passes through the vortex without being imparted any phase shift and floods your final focal plane with unwanted starlight. In practice, astronomers deal with this by sticking a polarizing filter downstream of the vortex, but this also has the consequence of removing half your throughput, which is a pretty bad hit to take when you want to image something as faint as an Earth-like planet. An alternative is a scalar vortex. This is commonly comprised of an etched dielectric material, so think of a sawtooth pattern cut into glass. And these have the limitation of being highly chromatic while they are polarization independent. Though in recent years, there's been some pretty cool improvements. So if you didn't see Nia T. Desai's poster, you should check out some of these new designs they have. So if I wanted to design my ideal vortex for HWO, I would want it to be scalar. I would want it to be high transmission. I would want it to be achromatic. And if I'm being a little greedy, I would want it to be relatively cheap and accessible to fabricate, so that we could iterate on the design, fabrication, and characterization processes over and over again until we achieve a really high performance result. And that might be possible with metasurfaces. Metasurfaces are arrays of nanoscale structures that can manipulate the phase, the amplitude, the polarization, and/or the wavelength of light. They can do so based on their size, their shape, the space between them, and/or their material. And they operate through a variety of mechanisms, namely different resonances, as well as propagation and geometric phase. But because most of my work focuses on propagation phase scalar devices, those are the main ones that I'll discuss in this talk. So how do they work? Quickly, we'll look at a single unit cell, which is a nanopost and its surrounding patch of substrate. In the scalar case, we want axial symmetry in our unit cells, so a square, a plus, or a circle, or any shape with similar symmetry. We'll fix the height to be compatible with fabrication techniques, and we'll vary the width of the posts. Changing the width changes its effective refractive index, which then changes the phase shift it imparts on incident light. So if you have a library of posts of different sizes, then you have a library of different phase shifters you can distribute according to whatever optical function you want to impart. For example, if I distribute my posts in a charge-to vortex arrangement, as shown in the cartoon on the right, I can transform an incident beam into a ring-like shape, all in a wafer-thin, wafer-light optic that's accessible to manufacture at academic clean rooms throughout the world. And so that brings me to the work that I have done over the past couple years. When I started working on metasurfaces, there was only even less than a small handful of people thinking about them as it relates to direct imaging of exoplanets. So even the most basic questions were largely unknown. Could we make a device that we were satisfied with in simulation? Could we actually fabricate the thing? And if we could we characterize it and prove that it works? And so one by one, I've answered these questions, and I'll go through each in some briefness for interest of time. So first, for design, I wrote an optimization software that lets us design achromatic, high-transmission metasurfaces. I won't go into the details of that. I'm happy to answer questions, but I'll highlight one innovation, which was in my 2023 SPIE proceedings. I introduced that optimization software, as well as a technique where we use the periodic or the aperiodic spacing of nanoposts to improve the broadband behavior of these devices, which is in comparison to fixed-period metasurfaces, which are more commonly used. We demonstrated that our aperiodic devices in simulation get lower phase residuals, more achromatic phase residuals, and comparable or higher transmission than fixed-period comparison devices. Here I'm showing a charge 6 vortex for the J band, but we also showed that this is wavelength agnostic. We showed it for J, H, K, and V for vortexes of different charge. And we showed that you also get some gains using multiple shape nanoposts in terms of achromaticity. Naturally, with the goal of HWO, we wanted to focus our efforts a lot on a visible vortex design. The goal was to, of course, get 10 to the minus 10 or better contrast in simulation over a 20% bandwidth, but as we all know, that's pretty hard. We did succeed in getting a vortex simulation where the vortex has very low phase residuals, very high transmission, and in my 2024 SPIE proceedings, I did a deep dive into what might be limiting our contrast. I'm going to skip over those results for interest of time, but I'm more than happy to answer questions on that. Which leads me to the next big question that I had to answer was fabrication. We might not have made an HWO quality design, but we made several that we were happy with and were ready to try making them. So could we fabricate a metasurface? The short answer is yes. The slightly less short answer is yes, with a lot of painful hours in the fab and a lot of time spent. And ultimately, these efforts culminated in a paper I led in a fabrication journal where I showed that you can actually make near-infrared 2-pi phase control metasurfaces with mass manufacturing techniques like photolithography, which makes it really easy and cheap to make large-scale optics compared to conventional electron beam lithography, which is very slow and expensive. So with the creation of some devices that we were happy with, it was time to answer the last question, which is, could we actually measure these devices and show that they work? The first thing we sought to measure were the same properties we used to actually design the metasurfaces. So that is the phase and the transmission. Here I'm showing a charge 4 scalar vortex for the H band that I described in my paper in 2024 in Optics Express, where we show achromatic phase and high transmission with some room for improvement over about 2/3 of the H band. With that, you could say we had created this long-term goal of a feedback loop between design, fabrication, and characterization, where each step could then feed off the other to improve our results. But we still weren't quite satisfied because we didn't know how our device would perform as a coronagraphic optic. And so in that regard, much of my recent work has been spent on the moderate contrast testbed. This is a testbed that we've built in the lab at UCSB with lots of help from these folks, some of whom are in the audience, so big thanks to you guys. And we've used this to measure our vortex. So here's an actual on-bench image of the testbed. There's a picture of the vortex and its mount. And just for fun, if anyone wants to see one, I brought one with me. And here's some actual results. So in monochromatic light, our vortex in or coronagraphic image is on the left at 1 wavelength. Our no vortex or non-coronagraphic image is on the right. And qualitatively, you can see clear suppression in both the peak and the area rings. More quantitatively, we can look at radial profiles of these images and see that the red non-coronagraphic radial profile is clearly much higher in both its peak and area rings than the sampled wavelengths throughout the H-band, which are represented by the blue radial profiles. From these profiles, you can take the region of 3 to 10 lambda over d and determine the contrast. And that's depicted by the curve in the right-hand plot, marked by the x's, where we cut contrasts of a few times 10 to the minus 5. So to put this into context, we tried to find the closest optic we could compare to that's on Sky, which was a charged 2 H-band vortex made of liquid crystals, which is in the Subaru instrument and was described by Kuhn et al. In 2018. So in their paper, they described or characterized their vortex over a 10% bandwidth in the H-band. And doing the same thing, we see our results, the dashed blue line, compared to their results, the gray line, are comparable or even a little bit better. For the full H-band, the overall results are comparable, where our null depth is a little bit worse. It's important to note that this is not an apples-to-apples comparison. These are different test beds with different detectors, but because there is no other metasurface coronagraphs, this was the closest thing we could find as a good benchmark. To add a little more context, this vortex was actually far from the best vortex we could fabricate. There are clear errors, in particular posts that are blobbed together, like you can see there, and slightly misshapen posts that directly contribute to dips in the transmission and also errors in the phase that are very correctable and will likely improve our contrast. To wrap up, I'll talk about a couple of new directions that I'm going. We've been working on a K-band vortex for the Scales instrument, which we've handed off and hopefully will be installed in the near future. I've also been doing a lot of PIA fabrication for Professor Sebastian Haffert, and here's a fun image of some squares. And even from that image, and this next image of our Charge 4 K-band vortex, you can see that now our fabrication process is off the chain, and we can make a lot of cool stuff. You can also see here that at the 2 wavelengths we characterized, the phase, if you can ignore those ugly imaging artifacts, the streaks in the top left image, and the transmission are a lot nicer looking. The transmission is more uniform, and so is the phase. So to wrap up, I will say I've gotten to do a lot of cool stuff. If anyone would like to have things made for them that they can put in their test beds or instruments, we're more than happy to do maybe some charity work or maybe some work where you pay us. Either one would be nice. But thanks so much for your time. Happy to take questions.
Really nice talk, Skyler. Sorry to step in front of you. Eric?
Hey, that was a great talk. Just wondering, how well do these metasurface things play well with like conventional optical coatings?
Like an AR coating, for example?
For example.
Well, the back side, because it's just made on a wafer substrate, of course, normal. The front side, it gets more complicated, but you can actually kind of design, you can build that into the design, is how I'd put it. So conventional optical coatings might be tricky, but you can actually add little caps on your posts, for example, that might act as an AR coating layer, or even add little structures under the posts that would do the same thing.
Okay, thank you.
Thank you for your interesting talk. So I have a couple of questions. So first, how your metasurfaces perform at oblique incidences. And also, I think you explained this, but could you explain a bit more, like if you compare liquid crystal-based, these vortex coronagraphs and metasurfaces, like could you like give comparison exactly how metasurfaces outperform and how they're better?
Yeah. Sorry, the first question was oblique incidences. I'll say we haven't tried it, so I'm not sure.
Is it important for your goal that they work at oblique incidences, or like how?
Well, for a vortex coronagraph, having a little bit of tip tilt is actually okay, as far as I understand it. And someone should please correct me if I'm wrong. But for other applications, I'm not so sure, and that would be a good thing to actually test. As far as liquid crystals go, the liquid crystals right now, of course, are outperforming us by a decent margin. And I think part of that has to do with there's only a small handful of us still kind of working on this metasurface stuff. And like the one in my test bed was really a first generation optic. We didn't even, the one that I showed for K-band, we didn't even characterize yet. So maybe that'll be an order of magnitude better. That would be pretty cool. But there's a lot of improvement that's already happening. There's one of my colleagues at JPL, Lorenzo Koenig, has a design that's, I think, hit the noise limit on one of their test beds. So the improvement, we'll say, it's on the upward trajectory, but because liquid crystals are a lot more mature, they're currently still doing better. I think that the key differences and thing that make scalar vortex with metasurfaces promising is you can make them achromatic, and you can also maximize the throughput, so you don't have to stick a polarizing filter in and lose a lot of light.
Thank you.
All right, let's thank Skyler again.